Okay, hello guys. Let's continue our discussion on compact operators on Hilbert spaces. As you can see here, uh, actually the lectures here are not prepared. It's just a summary of what we want to say. So I have prepared the note here for you, starting with this. If you remember, we already talked about the compact operators on Banach spaces, right? So here we are going to talk about the compact operators on Hilbert spaces. Of course, this is a particular example because every Hilbert space is a Banach space. So we are going to talk about the compact operators on Hilbert spaces, which are actually kind of Banach spaces, of course. If you remember, if we have a here H denotes any Hilbert space, okay, remember. If you have a linear operator on a Hilbert space, H, linear operator, we said that if the closure of TU, what is U? U is the open unit ball in H, okay? Open unit ball in H. If you back, if I'm not mistaken, on page 49, you can see the definition. We already discussed. So if the closure of TU is compact as a subset of H, then we say T is a compact operator. And if you remember, we mentioned that if T is a bundled linear operator on H, T is a bundled linear operator, okay? Belongs to B of H, it means bundled linear. And the dimension of the range of T is finite. If you remember, such operators are called of finite rank. I mean, when we say we have a finite rank operator, it means the dimension of the range of T is finite. Then T is compact. If you remember, we talked about this as a theorem without proof. Okay, now we are going to give you a particular example about the compact operators. Of course, we are going to introduce some kind of compact operators such that the dimension of the range is 1 actually. And of course, they are compact. Look at the next page. Yes. Here, you suppose that X and Y are two non-zero elements of this Hilbert space H. Using this X and Y, we define an operator denoted by this X tensor Y bar. Okay, this is the notation. X, read it tensor. Okay, tensor. T-E-N-S-O-R. Tensor Y, X tensor Y bar. We are going to define this to be an operator on H. Okay, we define like this. X tensor Y bar as an operator maps every H here to, look at here, the inner product of H and Y as a scalar times X. So simply this is defined to be a scalar product of X, but that scalar is given by this inner product. We can show that this operator is a bundled linear operator on H. Okay, bundled linear operator on H, and it is finite rank. It means the dimension of the range of this operator is finite. It is actually equals 1, so definitely it must be compact. You remember, finite rank operators are compact. Look at here. I'm gonna leave it to you to show that this is linear. Okay, linearity is easy, so you should be able to figure out. So I'm gonna leave it to you to show that this operator is linear. Now I'm going to discuss and show you that this operator is bounded and the dimension of the range of this operator is 1, so it is compact. But the linearity, I leave it to you. Look at the next page. Okay, here we want to show that this operator is bounded. Okay, look at here. The norm of X tensor Y bar H for every H equals the norm of Okay. The inner product of h and y times x. Okay. Now, by the property of the norm, this is a scalar, right? This is a scalar. This equals the absolute value of the inner product of h and y times the norm of x. Now, this is less than this. So, what is happening? Why we can say that? Why can we say that this is less than equals the norm of h, the norm of y, the norm of x? This is due to Cauchy-Schwarz inequality. Do you remember we have Cauchy-Schwarz inequality for the inner product, which says that the absolute value of the inner product of h and y is less than or equals the norm h, norm y, and this is itself norm x. So from this discussion, you agree with me, look at here, we get this. The norm of x tensor y bar, h is less than norm x, norm y, the norm of h. Look at here, you view this as a positive number like m. So what do you see here? The norm of x tensor y bar, like if you view this as an operator like t, the norm of t of h is less than m, the norm of h. This is true for every h. So what does it mean this? It means x tensor y bar is a bounded operator. Then you show that it's linear, okay? I leave it to you. So far we know that this is a bounded linear operator. But we want to show that the dimension of the range of this operator is 1. So it's a finite rank operator. So by that theorem it is compact. Look at here. Look at the formula or definition of this operator. Look at here, it maps h to, look at here, the inner product of h and y times x. So if you look closely, you can see the image of this operator, look at here, is given by the scalar product of x. When here h runs over the Hilbert space h, we can have the scalar product of this element x. So roughly speaking, we can see that actually the image of this operator or the range of this operator is a one-dimensional subspace spanned or generated by x. Okay, more precisely, if for every scalar alpha I take h to be, look at here, alpha over the norm of y squared times y. So it means h is a scalar product of y, element y. And look at here, since y is non-zero, so the norm of y squared is non-zero. So this makes sense. So now look at here, this operator maps h to this, and h here is this one, right? Okay. You can see the inner product of these two times x. Now here, by the property of the inner product, you know that the inner product with respect to first component is linear. So this moves out, so becomes alpha over norm square, the inner product of y and y, this is scalar times x. But look at here, the inner product of y and y is norm y squared. So this simplified by this only left alpha x. So what is the range of this operator? We can see a scalar product of x. So the range of this operator is alpha x. Alpha belongs to a scalar field, complex number. So what is the range? The range is actually one-dimensional subspace of H, our Hilbert space, spanned or generated by this element. You can see when you say the scalar product of X, this is a one-dimensional subspace. So the dimension of the range will be 1. So it's a finite rank operator. So definitely this operator will be compact. In particular, look at here, in particular, okay, here. If our Hilbert space is L2, do you remember we talked about this Hilbert space, the Hilbert space of all S-squared summable sequences of complex number. Now you take this element of L2, E1. E1 is one of the elements of the basis for L2, right? If you remember, L2 has a alpha normal basis. This is E1. Now we define, look at here, E1 tensor E1 bar, which is definitely a compact operator on L2 because this is a finite dimensional. It's a finite rank operator. Okay. So for example, when we say E1 tensor E1 bar maps every element here to an element here, right? How does it do this? Okay, the inner product of x, look at here, inner product of x and E1 as a scalar times E1. But look at here, x is a sequence, E1 also like this, right? This is x, this is E1. So the inner product of these two will be, actually, if you remember, we talk about the inner product on L2, x1, okay, this is a scalar. So the inner product will be x1 times E1. So what does it mean? It means the one-dimensional subspace of L2 spanned by E1. It means this, x1. So you remember, like x1 times this, x1, the rest 0. So we can see the range of this operator is the one-dimensional subspace of L2 spanned by E1, which is naturally is isomorphic to C, complex number. So you can see this. So this is an example. Of course, this is a compact operator, and actually it's kind of projection. This is a projection. We can view this as a projection of L2 onto one-dimensional subspace of L2, which is naturally is isomorphic to C. And at the end, look at here. Okay. Look at here. Yeah. The set of all compact operators on a Hilbert space H is denoted by K of H. Okay, it means basically when B of H it means that the set of all bundled linear operator. Okay, so when we are talking about compact operators, it means compact linear operators. They are automatically bundled. So the set of all compact operators is a subset of B of H. Okay, because every compact linear operator is bounded. We can show that this K of H is a closed subspace of B of H. It's a closed subspace. Okay, so since it is closed, it is complete, right? So it means K of H itself is a Banach space. So it means compact operators as a subset of B of H forms a Banach space. Okay, and in particular we have this. Look at here. This is very important. We mention these things without proof. At least bear in mind. If T and S are two compact operators and lambda is a scalar, this is interesting. S plus T is compact. Lambda T, it means the scalar product of T is compact. S times T, St, it means SOT is compact. And in particular, the adjoint of T is compact. This means the sum of two compact operators is compact. The scalar product of every compact operator is compact. Okay, the product, which means the composition of two compact operators, is compact, and in particular, more importantly, look at here. The adjoint of any compact operator again is compact. Okay, it means if T is compact, its adjoint, it means T star is also compact. So I think this is enough. I mean, it was a kind of introduction to compact operators. And actually, we can show that the compact operators are spanned by finite rank operators. Okay, so it means the closure of the subspace of B of H spanned by finite rank operators will be compact operators. But that's enough. Okay guys, next we are going to talk about calculus of variations. Actually, this is an introduction to the calculus of variation, that we are going to talk about the first variation. The discussion is really easy, maybe the easiest discussion that we have. And as you can see here in the lecture note, I provided enough explanation for you. So I believe that you can read it by yourself It's not big deal. Eventually the bottom line is we are going to solve a second order differential equation, so it's not big deal. So the explanation is enough here. I'm gonna leave it to you. So I just explain you something briefly, so do not worry, the discussion is really easy. I believe that if you read by yourself you can understand, so do not worry about this. But let me just explain you the summary here at the end, almost at the end. Look at here. You consider this functional f. F is a functional which maps every smooth function to a number, complex number, or a number, a real number. Here when we say y is a smooth function, it means it is continuously differentiable at least twice. So you can see f maps y to this. Of course, if we have the formula of y, we can calculate this integral, will be a scalar. Okay, what we want to do is this. We want to find a smooth function like y which minimizes the value of this functional, okay, subject to these two boundary conditions, okay, because the solution may not be unique, but when we consider the boundary conditions, the solution will be unique. So here is the problem. We have this functional, and remember this functional is not necessarily linear, okay, so this functional may not be linear. We want to find a smooth function like y on this interval, okay, such that the value of f for that y is minimal, okay, subject to these boundary conditions. Easy. Look at here, we have a theorem. If you are given such problem, if you want to find the solution, it means if you want to find y, you solve this differential equation. This equation is called Euler-Lagrange, okay, Euler-Lagrange differential equation. Look at here, the derivative of f with respect to y minus the derivative with respect to x of the derivative of y, the derivative of f with respect to y prime equals 0. So look at here one more time, I read it for you. Derivative of f with respect to y minus, here is derivative with respect to x of the derivative of f with respect to y prime. If you write down this, you will get a differential equation of order 2, okay. Then you, with respect to y, it means y is a function, or is a dependent variable, x is independent variable. So you solve this equation subject to this boundary condition, okay. Then the solution of this differential equation will be a smooth function which minimizes the value of this function. That's it. I mean, this is the summary of this chapter. It's very easy actually. So this kind of problem is called variational problem, and this is the first variation. Why? Because we have the, the derivative of order 1. If we have derivative of order 2 is second variation, so we can have higher variational problem. So that's it. Regarding this, so remember, regarding this, you can see here, I prepared one example for you and one exercise. So we are going to discuss one of these two. It doesn't matter, it's same. For example, I'm going to solve this exercise, discuss this exercise for you, and I leave this example as an exercise to you. As I said, it doesn't matter. So I'm gonna discuss this one and leave this one to you. Then actually we are done with this chapter, okay? We are done with this chapter. Now let me mention something. You can see our last chapter is stability and bifurcation, okay? Listen very carefully. I'm not going to discuss this chapter for you. Actually, I'm going to leave this chapter to you as self-reading, okay? So do not worry. this chapter will not be in final exam and also will not be in QE, qualifying exam. So do not worry. So this is our last chapter. I leave it to you for self-reading. Of course, you may need it. You should read and learn. Enough explanation is provided here. So I leave it to you. But do not worry. It will not be in final exam and it will not be in qualifying exam. So actually we are done. So that's it. Now let me discuss this variational problem. You can see, consider the variational problem of the minimization of the functional, is functional subject to these boundary conditions. So as I mentioned, we are going to do this. We are going to write down the Euler-Lagrange of this variational problem, solve this. You will see this is a differential equation of order 2, ODE. Solve this subject to boundary condition, then we will find the solution of this variational problem. So I'm going to discuss this one for you. So let's do it. Okay guys, now as an example for variational problem, I'm going to discuss this exercise for you, and then you can work on this example by yourself. So I leave this one as an exercise to you. So we have a variational problem of the minimization of this functional subject to these boundary conditions. So we want to find a smooth function like y which minimizes the value of this functional. Okay. Look at here, I have done here for you. This is our functional and these are our boundary conditions. And here you can see this is actually y squared minus y prime squared minus 2y is our function f of x, y, y prime. Of course you do not see x here, but in general we consider this as a function of 3 independent variables like x, y, y prime. Now to find the solution of this variational problem, we write down the Euler-Lagrange equation, this one. Okay, so the derivative of f with respect to y here, with respect to y, so it means this is like number, so this is 0, derivative of y squared is 2y, this one 0 because we said derivative with respect to y, and derivative of this one is minus 2, minus derivative with respect to x of this. Okay, this one is the derivative of f with respect to y prime, right? Okay, this one is 0, this one is 0. Look at your derivative with respect to y prime. So derivative of this one with respect to y prime, okay, becomes a 2y prime. Now so 2y minus 2 minus, okay, here we have 2y prime. Now we have to take the derivative of this 2y prime with respect to x. Of course, y prime is a function of x. It's the first derivative of y. So when you say the derivative with respect to x, since this is a function of x, it means the second derivative of y with respect to x. So we have 2y minus 2 minus 2, okay, this 2 is a constant. One more time derivative, right, becomes the second derivative. So becomes 2y minus 2 minus 2y prime here, okay, because this becomes the second derivative of y here. So after simplification we get this y double prime minus y equals minus y double prime minus y equals minus 1. Now you can see we have a second order linear ODE. Now we have to solve this to find y subject to these boundary conditions. So here you can see I have done it for you. Yes, here. So we have this second order linear ODE that we have to solve it subject to these boundary conditions. Because when you find the answer has a particular part and homogeneous part. And in homogeneous part you will have two parameters like C1 and C2. So these boundary conditions are will be used to find those parameters. And you can see here we have to solve a differential equation. So here is my warning to you. You need to recall all stuff on the differential equation on ODE. You will need it, okay? So you have to recall the stuff that you have learned from differential equation. Okay, if you remember, first we have to solve the homogeneous equations. So y double prime minus y equals 0, and this is the auxiliary equations. The auxiliary equation, and the root of auxiliary equation, we have two distinct real roots, plus minus 1, right? Okay. So we get two linearly independent solutions for homogeneous solutions. So we have y1 equals exponential x, y2 exponential minus x. Okay. So the homogeneous solution will be the linear combination of these two. Now we have to find the particular solution. It means a function usually denoted by yp, which satisfies the non-homogeneous equation. And you know that to find yp we have two methods: UC undetermined coefficient, UC method, undetermined coefficients, and the other one is variation of parameters. But here you can see the right hand side is a constant, so it is easier to use UC, undetermined coefficient. We look at the right hand side. Our right hand side is a constant, right? So we guess that yp must be of the same time, constant. So yp equals a constant like a. And we have to be careful that no homogeneous solution must be here, and you can see no homogeneous solution is here, so this yp is safe and correct. So yes, now we know that now this yp must satisfy this, right? We put yp here to find a. So we know that since yp is a constant function, the first derivative and second derivative are 0. So now if we put the yp here, it must satisfy the non-homogeneous equation. So yp double prime minus yp must be equals to minus 1. Must be equal to minus 1, and you can see this is 0 minus, and this is a equals minus 1. From here a equals 1. So yp is 1. Now the solution is yp plus yh. It means the particular part or solution, which is 1, and homogeneous part, which is the linear combination of y1 and y2. Okay, this is our solution. Now we have to apply the boundary conditions to find C1 and C2. Okay, here C1 and C2. Okay, y at 0 is 1, so this gives this equation. Y at 1 must be 0. Okay, you can see this gives this equation. So we have a system, we have to solve it. You can see I have done it here for you. If we solve this system, it's easy. We get C1 is this and C2 is this. So at the end, y equals 1 plus, this is C1 exponential x plus C2 exponential minus x. This is the solution to this variational problem. It means this is the function for which the value of this functional will be minimum. Okay, like this. So you can see for variational problem, we have to solve the differential equation. So you have to be careful. You need to recall the stuff on the differential equation. You can see, because here when you want to solve the variational problem, the bottom line is you have to solve this differential equation, so you need it. So this was an introduction on variational problems, first variation that we discussed. And as I mentioned, the last topic is stability and bifurcation. As I mentioned earlier, I leave it to you as self-reading, and it will not be in final exam nor in QE. qualifying exam. So we are done. So, and here at the end you can see some references. If you want to know more, you may refer to these textbooks. So we are done. I wish you good luck on the final exam and QE. See you.